Now on to chapter 1, which is a math chapter. It's called Vector Analysis. In electricity and magnetism, it's an understatement to say we use vectors a lot. We use vectors continuously. Pretty much everything we talk about is in terms of vectors and vector equations. So let's just make sure we're all up to speed on vector analysis. The first part of the chapter, I'm not covering everything in this chapter. You really ought to know pretty much all of it already. But let's just review some of the most important points. Actually, the first thing is a pretty mundane point about notation, but I guess it needs to be said. On the board, I'm going to be writing vectors as letters with arrows on top of them. But in the book and in your homework assignments, vectors appear as bold letters with no arrows on top of them. When I am writing equations, I am writing exactly what I mean. When I'm talking about a vector, I use a vector symbol, and when I'm not talking about a vector, I don't use a vector symbol, and I hope you'll get into that mode too if you're not already. The distinctions to be made are between the symbol for a vector and the symbol for its magnitude, which is italic in the textbook, and I'm just writing a letter with no arrow on top on the board. I'm not going to do any bolds on the board. But another way of writing the magnitude of a vector is with two vertical bars. He also mentions dot products and cross products in this section, and I'm not going to mention them because I assume you're familiar with those quite well. In fact, I'm going to skip ahead to section 1.1.4. You should browse through this chapter and make sure that all the things that I'm skipping are familiar and under control. So this section is also mostly about notation. Let me draw coordinate system x, y, z. The origin is O. And here is a point whose position is defined by the vector r. R equals position vector of a point. That means that's the vector that would take you from the origin to the point in question. We could write the vector in terms of its components, and the position vectors have kind of strange notation for components. The x component of r is usually not called r sub x, but it's called x, and so on. And notice in this book, Griffiths uses x hat, y hat, and z hat as the standard unit vectors. The magnitude of the vector r is equal to the square root of x squared plus y squared plus z squared. And we could create a unit vector, r hat, which points in the direction of r, but has a magnitude of 1, by taking the vector r and dividing it by the magnitude of the vector r. That's basic stuff. Let's consider the so-called infinitesimal displacement vector. it takes you from the point with coordinates x, y, z to the point x plus dx, y plus dy, z plus dz. So the infinitesimal displacement vector, in this book he writes dl, little l, is dx x hat plus dy y hat plus dz z hat. And this kind of thing is used in some forms of integration, like line integrals. In E&M, we frequently find ourselves in the situation where we want to talk about two positions at once. There is what you could call a source point, which is denoted by r prime in this book. For example, where some charge is located, and what you could call a field point, denoted by r without a prime. For example, where you want to find the electric field. Where you're trying to calculate some fields. So, very often we need to refer to the separation vector, which in this book is denoted with a little script r. A cursive r, r minus r prime is script r. In other words, it's x minus x prime x hat plus y minus y prime y hat plus z minus z prime z hat. Script r without an arrow on it means the magnitude of the separation vector. And we very often need to refer to script r hat, which is the script r vector divided by its magnitude. Let's have a little sketch. Here's the origin and a vector r and a vector r prime, and script r points from r prime to r. So if you are trying to find the electric field at position r, and there's a bit of charge at position r prime, script r vector is the vector that points from the source to the field point.